for the introduction. So I guess I realized many participants in this workshop have the high energy background. So I hope that I'm a microscopic person and I focus on the UV lattice system. So I hope my talk will be the breath of fresh air just to take a break from the high energy system. So disclaimer, so I care about the gapped quantum phases in which the low energy theory is a TQFT. So I'm focused on the gapped system. And by defects or symmetries, I'm mainly talking about topological defect lines. They're all topological and they can be fit into a nice categorical structure. And if I do not emphasize 1 plus 1D, every dimension I say in my talk is about the spatial dimension. So there has been some previous work in studying the UV microscopy realization of the non-invertible symmetry on the lattice. For example, Kahn's state sum construction and also Lorentz and Kerr operators, they focus on the tensor network perspective. And recently, Sahan and Shuhan, they have a single lattice model realization of the RepD8 SPTs. And from the TQFT perspective or the categorical side, the classification of non-invertible SPTs is fully established for 1D fusion categories. So you just need to search for the fiber functors. So if you only care about the IR theory, you're done. And you just need to look for the fiber functor. And in fact, this is the first mathematical paper. They gave the anomaly-free condition for the fusion category. It's equivalent to the fiber functor, in which they gave a functorial formulation of the TFT with defects. However, like I said, I come from the community of studying topological orders, and we cared about SPT as gap quantum phases, not just as a TQFT. So we care about the physical features of SPT in the lattice model. What that means is that first, we need to define the trivial SPT phase. In order to do that, we need to fix the symmetry action to be on-site. So in this talk, the first one we want to address is that we need to generalize the notion of on-siteness for non-invertible symmetry operators, because in general, non-invertible symmetry acts non-on-site. So we need a generalized notion for that. And then the non-trivial physical feature of the SPT phase is that the edge mode has some projected symmetry actions. So the boundary of the SPT is anomalous. And because I care about the lattice model, so I want to give an alternative classification of the SPT phase instead of just the fiber functor. So that will be classified as a matrix algebra. And finally, we realized that the stacking for non-invertible SPTs, they do not exist in general. So if that happens, like how can we implement the permutation of STP phases? So those are the main topics of this talk. So I will just give a lightning review of what an SPT phase is. It's the symmetry-protected topological phases. And in 1 plus 1D systems, so it's a gap quantum phase of matter that is short-range entangled. It can be trivialized to a trivial product state by a finite depth local unitary, but it has a unique gap ground state. When the symmetry is enforced, the ground state cannot be connected to a trivial product state through any gap symmetric path of the Hamiltonian. So this thing might sound very boring because it does not have any intrinsic topological excitations. But what makes this interesting is that it has the first systematic understanding how the symmetry itself can lead to robust and non-trivial quantum matters. So for the group SPTs, many efforts has been made in the past 20 years to understand its classification. So the boundary of the SPT order corresponds to the lower dimensional anomaly. And the classification, first we realized it's a group cohomology construction, and then in higher dimension, the full classification is given by the cobordism class. And there's also some microscopic classification called domain wall decoration. And for those high energy people, protected by symmetry means that it gives some non-trivial response when coupled to the background G gauge field. It is an invertible TQFT, means that it's a pure phase. So if you evaluate this action on a closed manifold, it gives 1. So that's the ground state. And I think for this one, of non-invertible S in 1 plus 1? I'm going to show that later. And this talk is about like how to construct that. Yeah, so you're talking about the field theory or the lattice model. But I'm getting to that. Okay. So since we want to discuss the symmetry, what exactly is a symmetry? So zero form symmetry is too special. We can have symmetry acted on extended objects in higher dimensions. So that's called a higher form symmetry. And those higher form symmetries can be intertwined, which will form the higher group symmetries. And some symmetries, it does not necessarily admit the inverse that will give a non-invertible symmetry. So instead of a group, we need a more general mathematical framework to characterize symmetries. Let's see an example for the rep D8 SPTs. So this is a cluster state model. This model is self-dual under gauging Z2 times Z2. When it's self-dual, it will have some enhanced symmetry. In this case, we have a non-invertible symmetry, which is D operator. It's very complicated. It's a string operator. And what makes this non-invertible, we can examine how this D acts on local operators. It maps X to ZZ. So on the left-hand side, you have product of X on the periodic chain, on the ring. And on the right-hand side, this ZZ, it goes to 1. So there's no way it's implemented by a unitary. That's what makes this operator as non-invertible. You can also try to compute the fusion rules of this non-invertible operator. So if fused to a sum of multiples, that makes it a non-invertible. However, we realize that there's a lot more to explore. First of all, the symmetry operator is too complicated. And it's better to write that in an MPO form to compute the fusion. And then a general non-invertible symmetry does not arise from self-duality. And we want a systematic construction for non-invertible symmetry operators and the Hamiltonians. And so, like I said, this operator, it does not act on site. And what does it mean to have an on-siteness condition for this kind of symmetry operators? And finally, the categorical coproduct might not exist for a fusion category symmetry, so the stacking structure is not there. When that happens, how can we permute different SPT phases? So for finite non-invertible symmetries, what that means is that the fusion would correspond to a direct sum of multiple symmetry operators. And this fusion is encoded by how the operators are mapped into each other. And I think that's the essence of the category theory. So we abstract the object itself and encode the relations by finding out how they are mapped into each other. So in a fusion category, we have the objects, in which the objects are just the topological defect lines. And the morphism space, you can think about that as a zero-dimensional defect that maps those topological defect lines. And it has some monoidal structure to implement the fusion. It's semi-simple, means that every object in the fusion category can be written as direct sum of some simple lines. And they each admit a dual, means that it's a topological operators. You can create a pair out of a vacuum and annihilate a pair into the vacuum. And the associativity holds up to a constant called the F symbols. The F symbols must satisfy a consistent conditions called the Pentagon equations. Like for example, if you have 4 objects, you can fuse them in different orders. Yeah.
So X turns like this cross product with Y is the fusion rule. So it's how two topological defect combines.
Yeah.
While the other function is morphism that takes 2 defects. What does it like? What is this junction? How can I imagine that?
It's a zero-dimensional defect. It maps defect to a defect. And then, for example, you have the fusion, that'll be Hom X tensor Y, comma Z. So it encodes, so like in general, the dimension of this Hom space is a multiplicity of the junction. Like for example, that's this N here. N corresponds to the dimension of the Hom space. So like I said, that the SPTs corresponds to the fiber functor, What's a fiber functor? So fiber functor is a monoidal faithful exact functor that maps from the fusion category to the category of finite dimensional Hilbert spaces. It is monoidal means that it preserves the fusion rules. And it's faithful means that it's injective in the Hom space, so there's no non-trivial morphism collapse under this map. And it's exact because it preserves the semi-simple structure of the fusion category. I should say that the fiber functor is defined for a general ring category or a tensor category, but for a fusion category, the exactness and faithfulness, they're automatic. So usually in the definition, we do not mention that, but it's strongly monoidal. So I mentioned in the very beginning of the talk, if you're an IR person, like you just need to look for the fiber functor and you're done. So that's the classification. But as a microscopic person, so we need to look deeper into how this fiber functor can give me all the structures I need to write down a lattice model. So first of all, let me explain the physical meaning of this fiber functor. So it forgets the topological defect lines, but remembers its action on the ordinary Hilbert space. So we realize the symmetry lines on the finite dimensional local Hilbert space, such as diffuse according to the fusion rules in your fusion category without producing any anionic structure. So there's no intrinsic topological orders. Or in the continuum, you can think about this fiber functor as a tensor functor from the UV theory to the IR theory. So this means that your IR theory admits a trivially gapped ground state.
I don't understand the first sentence that you said. So can you give a little bit more context? So what does it mean to forget? What do you define forget here?
Yeah. So it maps the objects in C to objects in the Hilbert space in a controlled way. Because it's strongly monoidal, it comes with the isomorphism that preserves the fusion rule of the C. But eventually, the fusion rules, they're implemented by these objects in the Hilbert space.
And that's the forgetting then?
Yeah. It forgets the action, because every fusion category by Tanaka duality is equivalent to rep H. You're forgetting. Is it? Sorry, anomaly-free. Anomaly-free, yeah. Or like in general, a fusion category has a weak fiber functor that will give you a weak Hopf algebra. Sorry, yeah. In this talk, also, by fusion category, I mean those fusion category with a fiber functor. And by Tanaka, you have a rep H. This forgetful functor forgets the action on the Hilbert space. Yeah, so there's a bijection between the fiber functor and the C module structure on the module category. If you have a single object, and that's vec. And a module category characterizes the ground state of a gap phase. So I mentioned this Tanaka thing. So with this Tanaka duality, I use the fiber functor and take the coend to get a Hopf algebra out of it. And that will help me to implement a microscopic action on the Hilbert space. So why do we need a Hopf algebra? So this Hopf algebra generalizes the notion of the group algebra. The group is a set with operations, but I want to work with Hilbert spaces and linear operators. So this group algebra is a universal linearization of the group. And Hopf C-star algebra is a generalization of the group algebra. What that means is that, so it has a multiplication, which will give you the fusion of symmetry operators. It also has a co-multiplication to encode how symmetry acts on the tensor product of states. And it has an antipode, which generalizes the notion of the inverse of the symmetry operator. And because I work in a physical system, I want to define a Hermitian conjugate. So this is the C-star algebra. So let's see an example of this. So if your fusion category is rep G, and the associated, you take the coend, and the Hopf C-star algebra is func G. It's the algebra of complex function on the finite group. And the basis of this func G is the delta function. It uses the multiplication is the first one and has a co-multiplication and it's an interval and there's also a star structure. So this one is kind of trivial, but if you, for a more general half C-star algebra, the co-multiplication is not necessarily group-like. Like for example, in the first two lines, delta x and delta y, if you, the co-multiplication is a sum over a bunch. So now we know the symmetry is encoded by the symmetry category, which is the fusion category, but it needs to act on some symmetry charges, which will give me the Hilbert space. And the symmetry charges should transform under the representation of your symmetry algebra. So I have this fusion category, and I take the coend, and I get a half C-star algebra H. And the symmetry category is the representation of this half algebra. And in particular, I will mention later, this Q system would give you the commuting projector model. And then this SPT, which in the IR on the categorical side is given by the fiber functor, but in the UV, that would be the matrix algebra. Okay. So before I define a model, so I need to start with the abstract spin chain. So I pick my metric space to be a pole set. The set has some binary relation. It is defined because I want to do a sequential inclusion of the algebra defined on a finite region. And my symmetry charge is the element in the representation category of the half algebra. So on each side, I put a representation. And to do the tensor product, I need to use the co-multiplication because I need to open up the half algebra to have it acted on the composite system. And the interaction for that abstractly, so it's a morphism in my charge category. And so it maps objects in the charge category to a different set of objects in the charge category. And that defines the algebra of local operators on a finite region. And if we want to make this very precise, we need to incur the definition of the net of algebra. So you just do the gradual inclusion and take the co-limit in the category of unital C-star algebras, or I should say you take the inductive limit. So that will give you the quasi-local algebra at a thermodynamic limit. Okay, I'll just give a very brief overview. What is the matrix product operator? So we start with this very complicated string operator, which would be very hard to use. And this MPO, basically, it will break down a very complicated global operator into a chain of local tensors with necessary virtual space correlations. So first of all, you have the symmetry operator acting on the outside system. And on each side, you have an incoming leg and an outgoing leg, both of the local Hilbert space dimension D. And you group that to have a D squared dimension thing. And then you just like regroup the matrix and do a SVD, singular value decomposition, and then do that process iteratively. And finally, you will get a contraction of local tensors. That will be the MPO. So this MPO, I will graphically denote it as this. So this superscript is the virtual bound index, and the subscript is the physical bound. So let me use the Tanaka construction again. So I take the coend of the fiber functor, and I can decompose the half algebra into a multi-matrix algebra, in which each sector is labeled by the irreducible representation of the dual half algebra. So I want to do a Fourier transform from the element basis of this half algebra to the matrix coefficient basis. So why do I want to do this? So first of all, I want to write down everything in MPO, so I need a matrix coefficient. Second, the co-multiplication of the half algebra is very complicated. By using this matrix coefficient basis, the co-multiplication would just become the multiplication of the matrix. Let me denote the basis of the half algebra symmetry to be E sub I, and then the dual basis of H dual as E superscript I. And I take the representation as an irreducible representation in this rep H dual, and I map the element basis of E sub I to the matrix coefficient basis. And this alpha and beta index the dimension of the E-rep. Like for example, if you have a two-dimensional E-rep, this alpha beta would go from like 1, 1, 1, 2, 2, 1, and 2, 2. Like I promised, if you transform your element basis into this matrix coefficient basis, and then the co-multiplication would just become very simple matrix multiplications. And that will give me the virtual bond index. But now I also need my MPO to act on the physical Hilbert space. And the physical Hilbert space is a representation of the Hopf algebra. So I take this rho as the E-reps of H, and I project that down to each irreducible symmetry charges. So this rho here would give you the physical leg, and this tau here is a virtual bound. Okay, so I'll pause here for a minute, just for you to look at the equations, and then I'll give an example of rep D8. Yeah.
Are you going to put any conditions on which, so H inputs in your physical space if you want to be alive? A bit tricky.
Yeah, that's true. Okay, so which one are you talking about? Are you talking about the E-reps of H dual or E-reps of H? The physical leg or virtual one? That's true. Like for the rep H8 case, I do have 5 options for that. But rep H8 is a bit trivial because it has only one SPT phase.
Yes, but I think that if I remember correctly, there's 4 one-dimensional and 1 two-dimensional ones.
Yeah, yeah.
If you take any of the one-dimensional ones, I don't think that's the action of the rep D8 symmetry on that Hilbert space.
Rep H8.
Rep H8, sorry. It's rich enough to really see that it's
Non-trivial.
faithful representation.
I see. We didn't look into that because rep H8, there's only a product state. Like how can you see if this like a trivial or non-trivial? Yeah. For other cases, we didn't consider. Like the example we computed is rep D8, but rep D8, the charge category is like rep func D8 is equivalent to Hilb D8, so it's just a D8 graded Hilbert space. Yeah.
But even in that case, you need to pick the generator of the group of the your Hilbert space, otherwise it just doesn't capture this full symmetry. Okay, we can chat that.
Okay.
What's your notation for this Hilbert space? B minus 2, B minus 1?
Oh, it's the -2, -1 is the location, like the lattice site. And the V is the vector space, Hilbert space.
Is this some schematic picture where you have like 5?
Oh yeah. So like the actual lattice is a lot bigger. I'm just showing like 4 sides, 5 sides on it. Yeah.
Some arbitrary origin?
It's arbitrary. Like there's no like specific meaning to the number. It's just the order set. So the set has to be ordered. Otherwise, I don't have any other constraint.
2 numbers, 1 and the P subscript 1.
This 1 is the lattice site, and V1 is the Hilbert space on lattice site 1.
So all of these vector spaces are isomorphic then?
They're all irreducible representations of rep H.
The same representation?
It is the same. Yeah. So for example, you have H8, that's an 8-dimensional Hilbert space. Like Lorentz said, like you have different choices for this E-rep. You just pick one choices for this E-rep on each site. And on each site, that will be an 8-dimensional Hilbert space. And the element in there is our irreducible charges. elements, like in rep H. So H8 has 8 elements, and you pick an E-rep for each element, and this E-rep is the symmetry charges. Okay. Okay. Yeah, I hope this example will clarify some confusions, but this example is easy because the representation category of func D8 is monoidal equivalent to Hilbert D8. So on each side, I just have this 8-dimensional Hilbert space is D8 graded, and I can pick the E-reps for this D8, so it has 4 one-dimensional E-rep and 1 two-dimensional E-rep. Okay, so there, what that means is that, so this virtual bound goes from the index of the E-reps, and on the physical bound, because it's a DA graded Hilbert space, it just projects down to each symmetry charge. There, the symmetry charge is just the elements of this DA graded Hilbert space. And maybe we just see an example of a non-invertible symmetry operators. So you have this trivial rep for E is just the identity matrix. The one element there is 1. And then this S matrix is by X, so it's 0, 1, 1, 0. So this so the first column is 0. So just do that process for all the E-reps of D8, and you will have the 8-dimensional Hilbert space. Any questions? I hope that clarifies. Okay, I'll just move on if that part is fine. That's the virtual bound index. And then to get the action on the state, we need to convert that to the physical bound. And after you convert it, we realize that those symmetry operators act as E-reps on the physical state. Okay, are we all good?
Wait, so again, so your physical space is the group.
Yes.
It's an
Yep.
8-dimensional space.
Yes, that's the 8-dimensional.
Those are labeled by the units?
Yes. That's the matrix coefficient basis. So this one is the 8x8 matrix, but it's like if you convert it to the physical bound, it acts on it as the E-rep.
It's basis where it's diagonal, because you can go to a basis where this FU acts diagonal.
It's not a regular representation.
No. No, it's well, the way we understand it, I think, is you have on site a piece of freedom that labeled by group elements of the gate.
Yeah. Mm-hmm.
But that's diagonal.
Yeah. Mm-hmm. Mm-hmm. Confused? Yeah, I think I'll just move on. There's no more questions. But we did compute all the F symbols though. So, yeah. You have 3. H8 has 1. Q8 has 1. So D8 is a special one. Yeah. Okay. So this MPO need to satisfy the dualizable property. Like when it's satisfied, you can close the circle like to get a virtual bound dimension. And by the fusion rules of the fusion category, the outcome of this dualizable property is that if you have an on-site half C-star algebra symmetry MPO, then the virtual bond dimension is equal to the quantum dimension of simple objects. This property follows from the dualizable property, and that's how we define the generalized on-siteness condition for a non-invertible symmetry. And in fact, in the cluster state model by Sahan and Shuhan, that MPO is not in the on-site form. The virtual bond dimension is 4. So in their model, if you conjugate the CZ, you can make the MPO on-site. And when that happens, there is the trivial phase. That's a product state.
When you say on site here, you don't mean full dimension 1, right?
No, I mean the non-invertible, so the virtual bond should be 2. In their
The convention, at least to my knowledge, on site.
Yeah, that's why I said it's a generalized notion of on-siteness, because non-invertible symmetry operator, it does not act on-site. So you use that, yeah. It is on a tensor product over space. I'm not talking about the Wyckoff algebra, just anomaly-free case.
Yes, then on-site, or generalized on-site for you means that the MPO has minimal full dimension.
Yes, minimal. So, or you can say that MPO has to be dualizable. Like if you use the 4-dimensional one in Sahan's their paper, it's not dualizable.
So where is the name dualizable coming from?
Dualizable?
Yes. So what? So like this would only work for fusion categories that have integer quantum dimensions.
Yes. Yeah, sure, but like if it's not on site, the integer can be larger. Like in the cluster state paper, their virtual bond dimension is 4, but here it has to be 2 to be on site. I'm only talking about the anomaly-free case.
So there, say it's 4, it somehow reduces to this thing then?
You conjugate by a CZ, and you can reduce that to the on-site form. They picked the wrong basis because they got this model from the self-duality, so they do the gauging. Like when you do the gauging, there's a lot of freedoms for you to choose a basis.
I think they probably did like Grams-Ronier, then something, and then another one.
Yeah. Also, just from the cluster state model, it's obvious it's self-dual under gauging Z2 times Z2. Like if they do not have this canonical construction, it seems like it's okay for you to choose any kind of operator. But because we have this canonical construction, I can tell you the minimum thing, you should have the virtual bond dimension to be 2. And then you have to like put that into the on-site form.
So is your definition of on-site and what we call injective MPO?
No, like the injective, like they're all injective. But even when they're injective, you
Equivalent to 1 dimension 2. Injective means that you can get any matrix on the virtual level by acting on the 1 dimension 4, but it's secretly only 2. Then it cannot be injective. So injective is like.
So that one is not even injective? Okay.
If you conjugate it by CD,
Mm-hmm.
comes some virtual 1 dimension 2 operator,
Mm-hmm.
then it's isomorphic to some 1 dimension 2 operator plus some 0 operator.
Mm-hmm.
And injective means that it cannot be.
Okay.
No, but wait, the
But like-
conjugation that is done is not one.
No, I thought it was just on the virtual level. Conjugate with CD. Oh, sorry, the CD is on the physical.
Yes.
Yeah.
So
Because like this MPO, we check that, it's injective. There's also a different group people check that. They also, like, there's no problem with injectivity.
sorry, I thought you meant by conjugation. I thought you meant on
Yeah. Okay. Anyway, if that satisfies you, you can close that to a circle. Otherwise, the circle is not like complete. So if you put the right one to the left-hand side, so like this whole thing would be a circle in the middle. Yeah. Okay. Okay, there's no chalk, but like basically I want this thing to close. Oh. So I want this thing to close. Okay. Anyways.
Turn off the light again.
Yeah.
This one? Oh. Okay, great. So we have a generalized notion for this on-site symmetry operators, and then we can define the trivial phase. But this trivial phase is not necessarily canonical because the stacking structure does not exist for all the fusion categories. If the stacking structure exists, means that you have the categorical coproduct, and the trivial phase needs to be the co-unit. And when we have this on-site MPO, you can choose the basis to factorize that to the left and right part. And on each local tensor, this LS or RS, it acts on the projected symmetry charge. That'll be your edge mode. Okay, now with the symmetry operator, we can talk about the local interactions. So schematically, in a category, the interaction is given by the morphism to map the set of objects to a different set of objects. Normally, we want to have the symmetric operators as linear expansions for concrete calculations. When you do that, you need to project the objects into simple objects, and you choose a local trivialization to make this into a tree graph. But we have a more systematic way to do that. So for any linear map between two Hilbert spaces, we can define a symmetric singular value decomposition on the morphism space. And this map can be factorized through this image via this sequence of maps, where U and V are isometries, and the S matrix is a positive definite Hermitian map. And then after that, you just do the regular SVD on each of the matrix block. So for example, if I have two lattice sites, you do this decomposition, that will give you the interaction of two sites. And so if you do a F move, this thing would become a graph like this, acting on two lattice sites. That looks like you're transporting symmetry charge from one side to the other. However, that only gives me the interaction. I want a commuting projector fixed point model, means that I need to impose some algebra structure on the objects of the charge category. And it turns out this algebra is called a unitary separable Frobenius algebra, or in the subfactor theory, it's a Q system. And that gives me the commuting projector condition. So the Hamiltonian basically is written in this form. It's a multiplication and a co-multiplication. All right, let's see a simple example. It's for the Z2. In the Z2, your symmetry category is vec Z2, and the charge category is rep Z2. So the associated half algebra is func Z2. So we have those bases, and the Z2 acts on the state. So 1 goes to 1, and it does nothing, and this eta is the Z2. And by examining the symmetry action, you can put that into this A plus and A minus algebra. And you just do the multiplication and the co-multiplication of the bases, and that will give you the symmetry breaking phase of the Ising model. All right, are we all good for this example?
So it's a inner product giving
Yeah, if you combine that, it's just the matrix, right?
You expect also that there should be an X term, because at the end this is also symmetric.
Yeah, so here it's a symmetry breaking phase. The X term is func Z, E. Right. Yeah, you have other choices. Yeah. So so you have your charge category, and each gap faces correspond to separable Frobenius, unitary separable Frobenius algebra, and then you embed that into your Hilbert space. I just decompose that into a two direct sum of two algebras. A is an algebra. It's not a number. That's the basis. Oh no, that's a basis. I'm not taking the inner product. No. Yeah. Sorry, that's not an inner product.
So just if I understand, if I see that correct, so this in the end is the Ising model.
Yeah, it's a symmetry breaking phase of the Ising model. Yeah. Okay. This is multiplication and this co-multiplication. So I do the multiplication first and then co-multiplication. So you're multiplying all the bases in this algebra. Okay. Yeah, so because I want to write down the lattice model, previously I just tell you all the commuting projector models, like each gap faces corresponds to a Q system. But in 1+1D, we have SPT, we also have SSB phase. Like how do we characterize SPT versus SSB? So the physical intuition is that, first of all, the ground state degeneracy is a feature of the Hilbert space. We're not looking at this algebra, we're looking at forget A. So which means that when the symmetry is broken, we examine the ground state degeneracy. If it's a SPT state, the ground state is one-dimensional. If it's SSB, so it's not. But this is just the physical intuition, but we did prove that in the operator algebra framework to take care of the infinite volume limit carefully. So to do that, we noticed a bijection between the H-type ground state and the space of the fixed point operators. So first of all, let me define the screening map. The screening map would project out the high energy excitations, means that in your IR theory, any excitations generated by local operators should be invisible. And then I define this image of the screening operator to be frac Z of forget A. So for a Q system, which is already at a fixed point, the screening map is not going to do anything to my state. And I mentioned it's the H-type ground state because in operator algebra, their definition of the ground state is not the lowest energy state of the Hamiltonian. It's the lowest energy state within a certain super selection sector. So we need to be a bit careful with that. And then we first proved that the space of all the fixed point operators is isomorphic to the center of the algebra. And then we use a trick that, like, suppose you have a fixed point operator in the center, and we can define a C star, we can equip that with the structure of the commutative C star algebra. And with that, in this corollary, we show that this H-type ground state forms a simplex, and that established a bijection between the H-type ground state and the space of the fixed point operators. So with that, we can prove that any SPT phase correspond to a Q system when it's forget to Hilb, it's one-dimensional. So it's a matrix algebra in Hilb. So that will give us an alternative characterization of the SPT phase. Instead of computing by brute force of what the fiber functors are in your symmetry category, you can instead look for this matrix algebra. And that's actually a much more efficient way to find out the SPT phases. like for example, a lot of cases people are interested is when the fusion category C is rep G, and then your charge category is help G, and all the Q systems are classified into Morita classes labeled by the subgroup and the two-code cycle. You just list out all the algebras there and trying to compute which one is a matrix algebra. So for example, in rep D8, the matrix algebra is given by the trivial one, also two of the Z2 times Z2 subgroup. So pretty much use this trick. If your symmetry category is rep G, I can almost always immediately tell you how many fiber functors in there, because matrix algebra is relatively very easy to compute. Even for rep H, if you have a finite dimensional semi-simple Hopf C-star algebra, the Q systems are also fully classified. There's a theorem for that. Oh, by the way, also from the mathematical point of view, the trivial phase has to exist because I have this this trivial algebra.
Rep G define all subgroups that have just one projective representation with respect to some. Like the module categories of rep G are rep
Back.
H.
Yeah, that I know. Mm-hmm. Because I think matrix algebra is very easy to compute. You just need to list out all these algebras. And the matrix algebra, by definition, is central simple. You just need to compute the center of this algebra.
Okay, but you still need to figure out which second.
Yeah, but that's not hard. Okay, sure. Okay, but I think it's still a lot easier than computing the fiber functor of the symmetry category. Also, this thing has the advantage, once you find out the matrix algebra, I can tell you the dimension of the edge mode.
But as I said, so what you need to do is give you a group, you have to find all the cosines. Is that actually, why do you say this is easy?
Symmetric non-degenerate two circle. Okay. Probably all the examples I consider is like small groups.
Okay.
Yeah.
Because I think for big groups, it's not a question.
But computing fiber functor from the symmetry category is also hard.
Yeah, but okay.
Equally hard?
Side H.
Okay.
Restriction from G to H.
Yeah. Sure. Equally hard? Okay. Yeah, okay. Microscopically, I need this algebra as the input for my model anyways. So, and I have a different reason for that later, actually. So let's see the dynamics. So I have all three of the matrix algebras. So I take my physical Hilbert space. It's a D-graded Hilbert space. That's a large enough Hilbert space that I can embed all the gap faces into this Hilbert space. And I define a projection from this large enough Hilbert space down to each face. And I have this model that realizing all three faces at the same time. So let's take a look at the first non-trivial example of this rep D8. So there, I choose a different basis. I choose this basis so that my MTO can be factorized into left and right part, and there's a systematic way to find this basis, actually. So with this basis, okay, that's the MTO. It's factorized into left and right part. And then with this basis, we can, like, the ground state is the maximally entangled state. The effective Hamiltonian is basically just the one realizing that as a ground state. So that's a very convenient choice. But we did use the other, just the regular basis that recovers all the models constructed in the cluster state paper. All right, so the next question that we want to address is the permutation. So for rep D8, the categorical coproduct, which means it's this one, does not exist. which means that if you stack two rep D8 SPTs, you cannot define a diagonal symmetry action on two layers, so there's no the stacking structure. But that's weird, like how do we define the permutation of SPT faces? So from this paper by Yifan and his collaborators, we know that the three fiber functors of rep D8s, they're related by the monoidal equivalence acting on the symmetry category. Other than the monoidal equivalence, we also have the self-dual algebra objects. If you gauge that, that will give you back to the rep D8. So at first, we were a bit of confused because we saw that, oh, if you gauge one of the algebra objects, it might be able to permute the faces, but that's not true because permuting faces is implemented by the thing on the left, but not on the right. So in a separate project, we did compute how to gauge the algebra object of D8 that did not implement like the permutation at all. So in order to study the permutation, we need to understand the physical consequence of acting the monoidal equivalence on the symmetry category. So from a categorical perspective, we show that, like suppose you act a monoidal equivalence on your symmetry category, that will correspond to like induce an algebra in your charge category. And this category of AA bimodules is equivalent to the original charge category. Suppose all the fiber functors, they're related by the monoidal equivalence. But if that's not the case, the charge category is not preserved. So if that happens, you have different choices to realize your model. Like for example, we computed cases of rep S3 times D3. The forgetful functor, the trivial fiber functor, will give you the charge category as VEC S3 times D3, but the other one, the charge category is TYZ3 times D3. Okay, any questions?
Trying to understand. So you're trying to relate these different SPT faces to each other? You have different fiber functors.
That's for the case of rep D8.
Sure.
How can I implement that physically?
Right. So you have something that there's no algebra gauge.
It's not gauging because it's not gauging. It acts as the outer automorphism on the fusion ring. It's not implemented by gauging the algebra object. And we explicitly check that if you gauge one of the algebra objects, it does not permute a face. It puts the trivial SPT to itself, and the other two goes to SSB.
So actually that's my question. So these algebra objects, do they all give rise to different phases? Like, because there's different algebra objects that can basically give rise to the same topological phase.
Sorry, this algebra object means the gaugeable symmetries of rep D8. And those four are the one that you gauge that will give you back rep D8.
You're asking there's up to one Morita.
Yeah.
They're in Morita classes.
Yeah, so this is up to one Morita.
Yeah.
So they all give rise to different.
Yes, I think different modes of attack.
Exactly. That's the question.
Yeah.
That's not obvious.
No.
That's for the start.
Oh, that's the question? Okay.
Well, it's not obvious to me that all.
Oh, okay.
Algebra objects.
They're
There's
classified
like
into
many-
Morita
there's
classes, yeah.
Different algebra objects that can choose to gauge that give rise to the
Oh,
same.
no, it's already up to Morita equivalence, yeah. So that part, like the gauging would not help you to implement the permutation. So that's why I said that we need to study the physical consequence of acting a monoidal equivalence on the symmetry category. And it turns out that we induce an algebra in the charge category that satisfy this condition such that blah, blah, blah. So on the other hand, if your fiber functors are not related by this monoidal equivalence, it means that the charge category is not canonical. You have multiple choices to realize the model. Okay, so that's one example we computed. That's actually true for all the cases of and then the charge category is not preserved. I also like, okay. Those are the two examples, and there's also isocategorical groups. Okay. Are we all good with this statement?
This last thing, that's your notation for AA bimodules.
Yeah. CM dual is the charge category. Bimodules, yeah. So this AA bimodules thing is equivalent to gauging. Oh, okay, that statement would be confusing. So yeah. This A, all of these A's are matrix algebras, are the ones that I mentioned earlier.
Because you're already in this language.
So for fiber functor, you restrict this M to VAC.
I'm not talking about that. This category of AA bimodules.
Yes.
So the module got the equivalence between that one and itself, given by invertible bimodule category.
Oh. That I don't know the explicit module category, like simply because this algebra A is just one of the matrix algebras corresponding to the SPT. So I just compute that, but I don't know the module category because I don't think about that from the perspective. Yeah. Okay. Okay, so we just use that result to do the permutation. For rep D8, we know that all three fiber functors, they have this relation. So we compute the objects on the left and the object on the right. So the object on the right correspond to the original symmetry charge. Those on the left will correspond to the new symmetry charge. So we do an assignment, like see how the isomorphism explicitly maps. And because I know this A is a matrix algebra, I can write that into the form of W tensor W. So I write everything on the left, the object there, into the sandwich form. And in the middle, this V is the original charge from the right. Okay. After I decompose the objects there, I can correspondingly decompose the local tensors of the symmetry operators. So basically, we just need to examine how the tensors in the middle acts on symmetry charges. And then we realize that the action is actually different. So previously, I said that the symmetry acts as the E-reps of rep D8. When you do the sandwich thing, the E-reps are swapped. So that implements the permutation. And then we actually need to do the permutation. So we just sandwich the original algebra by the new algebra. And then there we can compute that all those faces are permuted. So basically, the message is that you cannot implement the permutation by writing down the gauging map or something, but instead, so we look at the physical consequence of see how those fiber functors are permuted, and we do that explicitly from the charge category from those matrix algebras.
It's the same doing some operation in the charge category.
Yes.
But that operation is not symmetric with respect to yours.
I don't know how to do that in terms of gauging. I don't know.
No, I don't talk about gauging. This state.
Yeah.
Fixed point state. It's operation that you're doing to itself charge category. It's what kind of operation would this be on that state? You know this?
We don't know. We really just computed from the algebra side. So like, or alternatively, well,
Changing this charge category to some one of the equivalent one, but you're doing it via some
yeah,
whatever.
yeah.
That's now vectors is like a circuit, but that would be actually symmetric with respect to the symmetry. So I don't wondering what you're saying is saying that these are actually not distinct SPTs.
Distinct, not distinct.
Because that operation that you're describing, at least to me, sounds like it would be symmetric with respect to your original symmetry C.
Yeah, but it's not unitary though. The Hilbert space changes. It's not unitary. It's definitely not unitary.
Like you would say that the cate state and the cluster state are also the same things, but the Hilbert space also the same. So it's not that simple.
No, I don't think so. Yeah. So yeah, that's my last slide. It's about future directions. So I think in this paper, we mainly studied the anomaly-free fusion categories. But in the future, it's actually ongoing work. We're writing the paper already to study the anomalous fusion categories. So the anomaly, the definition of anomaly in the UV system is that like usually the condition is that if I can realize the symmetry in the tensor product Hilbert space with on-site symmetry action. But suppose now I loosen the condition by allowing the symmetry by acting non-on-site. So you will have some like anomalous fusion category can be realized in the tensor product Hilbert space. Like for example, you have the CZX model that is realized as the anomalous boundary of the 2 plus 1D Z2 SPT. It's anomalous, but it's not on-site because the virtual one dimension is 2, but it's a group, it should be 1. And then can we violate that even more drastically? Like suppose if I can allow my symmetry operator to react non-on-site by mixed with translation, that will generalize the idea of Quarma-Swania. So we show that, so if you have some fusion category that is anomalous in the IR, but it can be realized in the UV system by allowing a non-on-site symmetry action, which we call that as a weak anomaly. So if you have a weak anomalous like fusion category, then the fusion category is necessarily weakly integral. And we also show that any weakly integral fusion category can be implemented in the tensor product Hilbert space by these duality channels. And then I also want to understand the anomaly inflow picture for non-invertible SPTs. Because previously, I think a lot of people have this misunderstanding that non-invertible SPTs are not invertible phases because we do not have the stacking structure. But in fact, the stacking structure is there for some fusion categories, but not all of them. So if that's the case, like how can we fit the non-invertible symmetry SPT into the cobordism hypothesis? Is that an invertible phase or a non-invertible phase? And then I think recently, like more people are interested in continuous non-invertible symmetries. But for now, it's just case-by-case constructions. And I want to see if there's a way to axiommatize the continuous non-invertible symmetries, like what category would describe that. Yeah, that's all. Thank you.
So we're talking about stacking. So how does the stacking of Majorana chains fit in this picture? That ketine fits.
Oh, yeah.
Something that you can understand from this.
Yeah. So that one is because my understanding of the stacking is either you have this categorical coproduct, or like if you look at the charge category, I have my interaction like this. I need this thing to braid so that I can stack that. So the charge category needs to be braided. For the case of the Majorana chain, because it's SVEC, so the Hilbert space is braided, so that one is fine, yeah. So it works.
So it means that it fits in your.
It does, yeah. But this one is strictly about like bosonic cases. We haven't started the systematic understanding for fermionic non-invertible SPTs.
And is there a complication or is it straightforward?
I don't think it's straightforward because we need to find out all the Q systems in the SVEC, and then like I need to have algebraic characterization for the SPD phase instead of SSB. So there is some like subtlety in there. Okay.